This is the lecture Introduction to HLSL and DXIL for Beginners, Part 4. So, originally, when I was creating this presentation, Part 3 and Part 4 were both in the same session. However, in retrospect, I decided to split them up into two different parts in order to be more easily digestible for the viewer, and also based on a logical subdivision of topics. For example, part 4 is entirely about transformation matrices. Now we will study transformation matrices, which is one of the most important things in computer graphics and HLSL shaders. So first, a little background of why we need these transformation matrices. In computer graphics terminology, a vector is a collection of three coordinates encoding a location in a 3D space. We represent it as an HLSL vector, of course. However, in order for these coordinates to have any meaning, we have to specify the origin. We have to specify what these coordinates are relative to. A 3D coordinate system with a specific origin is called a space. It's important to understand that a vector only makes sense within a coordinate system. If we don't specify the space, we can't represent any point. Transformations in a vector space are simply a change from one space to another. If we want to represent a transformation from one 3D space to another, we will need a float 4x4 matrix. In order to apply the transformation, we have to multiply all the vectors that we want to transform against the transformation matrix. If vectors were in space A and the transformation was describing a new position of space A relative to space B, after the multiplication, all the vectors would be described in space B. Many 3D transformations can be described using a 4x4 matrix, such as transformations between different coordinate systems, and also rotations, translations, scaling, etc. Multiple transformations that should be applied one after another can also be combined into a single 4x4 matrix by matrix multiplying them. The result is a single 4x4 matrix which encodes all of these graphics transformations. Then you can use that single matrix to multiply the input data by it, performing a whole bunch of transformations all in a single operation. So we have three float 4x4 matrices that enable transforming the model from one space to another. Each matrix enables a single transformation. Each transformation is implemented as a matrix multiplication, multiplying the position vector by one of these matrices. These transformations are transforming the 3D coordinates into other 3D coordinates, and then taking those 3D coordinates and projecting them into a 2D surface of the screen. You can chain several transformations together by multiplying the matrices one after another. The result will be a single matrix that encodes the full transformation. The order that we use to apply transformations is very important. First, we do the world matrix transformation, then we do the view matrix transformation, and then we do the projection matrix transformation. If we want to pre-compute these transformations once at the start, in order to save us processor time, we must do the matrix multiplication in this exact order because matrix multiplication is not commutative. So the model coordinate system of a single 3D model, also called a game asset in a 3D modeling software such as 3ds Max, Blender, or SketchUp, is relative to the 3D model itself. Usually, the origin is directly at the center of the 3D model. Now, the world coordinate system of a video game 3D level design with many 3D models is relative to the entire 3D scene. The world matrix transformation is basically taking the 3D model and placing it in the 3D game scene using translations, scalings, and rotations. Now the camera space is from the viewpoint of the camera / player, first person or second person. It is still a 3D scene, as you can see here. But all these objects are now placed relative to the position of the camera in the 3D scene. And all the coordinates are likewise mapped relative to the position of the camera. Now the view plane is a 2D surface of the screen, unlike the camera space, which is a 3D scene. The projection transformation goes from the view of the camera and takes that scene and projects it onto a 2D surface. So let's first go over the world matrix transformation. It is the first one. And so as you can see here, every model in the game lives in its own model space. And if you want them to be in any spatial relation, like if you want to put a teapot over a table, you would need to transform them into a common space, which is what is often called the world space. Once our model is exported from the tool to the game engine, all the vertices are represented in model space. Now, if we want to put the object we just imported in the game world, we need to move it and or rotate it to the desired position. And this will put the object into world space. So moving, rotating, or scaling an object is what we call a transformation. A world transformation matrix consists of three distinct kinds of transformations, being pre-multiplied together. The individual transformations should be done in this exact order. First, rotate the object into the correct orientation, and then translate it to where it needs to be in the world space. Also, you might want to apply a scaling operation to that object. So the first step when we want to render a 3D scene is to put all the models in the same space, the world space. Since every object will be in its own position and orientation in the world, everyone has a different model to world transformation matrix for that specific object, resulting in the teapots being independently scattered in the scene. When all the objects have been transformed into a common space, the world space, their vertices will be relative to the world space itself. Next step, we have the view matrix transformation. So with all the objects in the right place in world space, we now need to project them onto the screen. This is usually done in two steps. Step 1. Apply the view matrix transformation. Move the objects into the view space, which this slide is about. Step 2. Apply the projection matrix transformation. transform the view space into a 2D image, which is what the next slide will be about. Now, why do we need a view space? It enables us to simplify the math of the transformation and keep everything elegant and encoded into matrices. We need to render the 3D scene into a camera, which implies projecting all the vertices onto the camera screen, which can be arbitrarily oriented in space. The math simplifies a lot if we could have the camera centered at the origin and watching down on the scene along an axis, which implies that all the objects in the scene have to be oriented relative to the camera. This space is the view space, sometimes called the camera space, and the transformation we apply moves all the vertices from the world space into the view space. The job of the view transformation is to consider the effect of viewing the scene through a particular camera, such as a first-person shooter or a third-person or an isometric view in a video game. And during the gameplay, the camera may move around. So the most common way a view matrix transformation is implemented, as mentioned in the previous slide, we have a transformation matrix for each object that we place into the 3D world. The camera itself is considered as just another object in the 3D world, having a particular position and orientation from which it observes the scene. We have a transformation matrix to place the camera at a certain point with a certain orientation in the 3D world, just like any other of the objects. The view matrix is the inverse of that transformation matrix. So if you apply that view transformation matrix to all the objects in this scene in the world space, it would orbit them around relative to the position of the camera. So it's like the camera is observing them. Now, the projection matrix transformation. So the scene is now in the most friendly space possible for a projection, the view space, the viewpoint of the camera looking down upon the scene. Now, all we have to do is to project it onto the imaginary screen of the camera. Project out the depth or z dimension so that the three-dimensional view space or camera space primitives are reduced to two-dimensional screen space, also called clip space or projection space primitives. This converts the 3D coordinates of all the visible objects to be rendered in the view space into a 2D image view of the view that the camera sees. That is expected by the remaining bits of hardware that actually perform the rasterization and turn your triangles into sets of pixels. So to go from the view space into the projection space, we need another matrix, the view to projection matrix. And the values of this matrix depend on what type of projection we want to perform. So we can have a perspective projection or orthographic, isometric, or oblique projection. And all of these different kinds of projections, they each have their own individual view to projection matrix, whose values are based on what kind of projection to perform. Transformation matrices in HLSL. Transformation matrices are uniform float 4x4 variables, which means that they are common or the same to all of the input elements, vertices or pixels. They are set outside of the shader code in the C++ code of the DirectX app. The input matrices are coming from the code of the graphics app on the CPU into the GPU shader. Let's take a look at the code to declare a transformation matrix in HLSL. First, we have a data type. For an input matrix, it is always float 4x4. Then we have the name of the global variable. It can be anything. It can be the same name as the semantic binding, but it doesn't have to be. Then we have a mandatory semantic declaration, also known as a binding. These are the input matrix counterpart to semantic annotations for UI elements. Unlike the former, these semantic declarations are mandatory. They tell the CPU or graphics app which specific input matrix to load into this shader variable. Semantic declarations aren't arbitrary. They have to be one of the following. So we have a world matrix, a view matrix, and a projection matrix. Then we have a world view, which is a combination of world and view, and world view projection, which is a combination of world and view and projection in that specific order. So each category of bindings has a base, an inverse, and an inverse transpose version. These semantics determine the specific matrix that is loaded into the global variable. Now, you might have a question, is there just a world projection version? And the answer is no. The matrix multiplication has to happen in that specific order. You could pre-multiply the world matrix by the projection matrix, but the result would be meaningless and useless. Now, then we have these metadata members in the alligator jaws, less than sign and greater than sign. This metadata member determines the UI widget to be used. If we go back to the NVIDIA FX Composer, here we see the declaration of the worldview projection matrix. So notice, if we set the string UI widget equals none, then the input matrix does not have a corresponding input UI element. So if we look at the materials panel, we don't have any anything here, any materials here. If we, for example, change this, first let me set the UI widget back to color for this one. So because the UI widget is none, no UI widget is being displayed for the worldview projection matrix. Now, if we set the UI widget to something else, such as color or slider, I compile, it indeed shows a UI element, but it is read-only, unmodifiable, because the input matrices are special data that are given specific default values by the CPU, so you can't change them. If I then set this to slider, I compile, and I see the slider, but I can't modify the values in the worldview projection matrix because they are unmodifiable, uniform input. Let me set this back to none and save and compile, and we see that it hides the input element associated with this matrix, which is what we want, because it makes no sense to show the user a UI element for a piece of data that they can't modify, a piece of data that is supposed to be internal to the HLSL shader and that the end user should know nothing about. Now, this is a use case of input matrix. Out.position equals mul in.position, comma, world view projection. Onto the input vertex position, apply the world view and projection transformations and pass the output into the pixel shader. This line of code transforms the input position of the vertex from the object space or the model space, which is where it starts, into the screen space or the clip space as the output from the vertex shader. This mul is a special function used for matrix multiplication in HLSL. In.position is the position of the 3D object in object space or model space. World view projection is a projection matrix used for projecting the 3D scene as viewed by the virtual camera onto a 2D surface or screen. This is the model view projection matrix, which translates a 3D point in the local coordinate system of one object in the 3D scene into its final pixel coordinate on the screen. So it goes all the way through. Now, coming back, the subtle actions of the matrix multiplication that is performed behind the scenes depend on which operands are given to this function in which order. In other programming languages, such as MATLAB, for example, row vectors and column vectors are explicitly specified. In HLSL, however, is it a row vector or a column vector depends on how the vector is used in the code. So suppose we have a float 4 vector and a float 4x4 matrix, and we are multiplying a position vector by a matrix. So there are actually two forms, two different syntax styles, and they depend on the order that we provide the operands into this multiplication function. So we have float 4 output equals mul vector comma matrix. We have the vector on the left side and the matrix on the right side, and we're basically treating this vector as a row vector and then multiplying the matrix by it. And if we have the matrix on the left side and the vector on the right side, we have the matrix on the left side, and now the vector is on the right side, but it is treated as a column vector. So we're multiplying the matrix by that column vector. Now, another interesting point is that according to a property of linear algebra, this expression and this expression are equivalent, and this expression and this expression are also equivalent. So it means that when we provide mul vector comma matrix, we can also interpret that it is equivalent to taking the transpose of the matrix and multiplying that by the vector as a column vector. And this matrix comma vector is the equivalent to taking the vector as a row vector and multiplying that by the transpose of the matrix. So there's not really necessarily a fixed convention if these are inherently row vectors or column vectors. Depending on how you rearrange the computation in your shader code, you could interpret them as columns or as row vectors. But the data type itself doesn't have that information built into it. How you interpret what's a row vector and what's a column vector depends on how the mole function treats its operands. And even more so, because of using this property of linear algebra, if we want to treat the matrix as a transpose, for instance, we consider that the mole function does an implicit transpose behind the scenes as it's doing the matrix multiplication. HLSL does have a dedicated transpose function, but using this property of linear algebra is an optimization, eliminating doing an extra transpose. In any case where transpose is used, it is either pre-computed on the CPU side, such as this world view projection inverse transpose matrix, and sent in as a uniform data, or it's using the mole function in a certain way and interpreting the results in a certain way, which causes that basically this explicit transpose function is not that widely used in HLSL shader code. Now, as I mentioned before, the order in which you do these matrix multiplications matters. That can be confusing depending on the different conventions. If you're using a row vector convention, you put the matrices after the vector and multiplication is applied left to right. If you're using a column vector convention, you put the matrices before the vector and multiplication is applied right to left. Now we're going to take a look at some examples of transformation matrices in HLSL code. So in order to go all the way through the matrix transformation pipeline, we can either explicitly multiply the input position in model coordinates by a model to world matrix, then the world to view matrix, then the view to projection matrix, in that order, getting the final position coordinates in clip space. Or we can pre-multiply these three matrices to get the world view projection matrix. Then multiply the input position by the world view projection matrix to get the final position coordinates in clip space. This pre-multiplication is done on the CPU C++ code and passed onto the GPU HLSL shader code. So in HLSL, we have access to this world view projection matrix that we can just use. So here I am declaring four different input matrices. This one is the world view projection matrix. This one is just the world matrix. This one is the view matrix, and this one is the projection matrix. So here we want to see what happens when we just use the provided worldview projection matrix versus when we manually compute the worldview and projection matrix transformations using a row convention. So let's perform an experiment, test these two ways. We want to see if doing the manual computation gets the same results as just doing the worldview projection matrix that is provided to us by the graphics app. If the manual computation produces the same results, then our theory that the worldview projection matrix is the result of such a precomputation in the CPU is correct. How do we find out that they are the same? A valid matrix should transform the vertex position from the model space into clip space. If it doesn't do that exactly, then we would not be able to see the objects in the scene, in the video game. So if we go back to the directory where we extracted the archive, within that directory there is FX Composer and matrix transformation. So click on the project file and it should pop up in NVIDIA FX Composer. Give it a minute and it should appear. What we have here, we have a scene with several objects in the video game, and we have a material in the shader. And if I open it, we see all these four different transformation matrices that we talked about. In the shader struct, the input struct just has the input position, and the output struct has the output position and the output color. But the most interesting thing that we have is in the vertex shader. It creates a output struct and initializes the output struct with all zeros and then returns the output struct. Now, this first code, as we see, it just performs a straightforward matrix multiplication. It just uses the provided worldview projection matrix to calculate the position. And then this second line of code right here does the same, but it does a manual computation. Specifically, it does the manual computation using the row convention. So we take this in dot position and we treat it as a row vector. And then from left to right, we first multiply it by the world matrix, then by the view matrix, then by the position matrix. So we are getting the output position first from this position that we are just computing using the worldview projection matrix. So if we compile this, we are able to see all the objects. It means that the matrix transformation successfully takes each object and transforms them accordingly and puts them into the clip space that allows us to see the objects on the screen. Now, if instead of this position WVP, I replace it with position 1, which is the output from this manual computation. So I compile it, and we see that we can still see the objects in this scene. So nothing changed, but we are actually using this line of code instead. And just to prove that it actually works, I'm going to copy and paste this, and then I'm going to comment out this line, and I'm going to introduce a bug on purpose, where I'm going to first multiply the vector by the world matrix, and then I'm going to multiply it by the position matrix and the view matrix. so it's in a wrong order instead of the proper order. So when I do that, I compile, and notice the objects disappeared, but they didn't disappear, they just seemed to disappear. They're invisible. The objects are invisible because we did the matrix transformation incorrectly. A valid worldview projection matrix transformation projects the objects from the 3D space onto the screen, and because we don't see the objects on the screen, chances are that it projected them somewhere way off the screen, way off of this screen, which means that we cannot see the objects anymore. However, they are still there because like if I just delete this line and bring back the valid position 1, I bring it back and I compile, we are able to see all the objects, including this sphere that I just previously selected. Okay, so now we are sure that they are the same, at least functionally. But what is the difference between these two? Is there actually any difference? Well, the difference is in performance, because when we are using the worldview projection matrix, we are already getting a complete result out from the graphics app, and we are sending it to the pixel shader or to the vertex shader. So like here we already have a complete result. We didn't calculate it or anything. And when we are doing the manual computation, notice that we take the row vector and multiply it by the world, the view, and the projection matrix. And even more so, it happens in every single input element, which is inside of every single pixel that you are processing on the screen, or inside of every single vertex of the 3D model. It happens. So if we look back, right here we see that we are performing this computation in the vertex shader, which means that we are doing it for every single vertex. But still, I mean, if we would just use the provided worldview projection matrix, we would be able to save 2 matrix multiplication instructions, which would be performance again, because as we will see later in the DXIL code, when we take apart the mul function call, it generates a whole bunch of LLVM instructions, which if we are able to cut down on the number of multiplications, the resulting DXIL code is smaller in size and also runs faster. So that's basically the idea of time versus space complexity, because you may be wondering why does the CPU provide us with all of these different kinds of matrices? Well, it's sacrificing just a little bit of space as an input parameter in order to save us the time of actually redoing that manual computation in every single pixel or in every single vertex. So by using some constant space, it saves us some time which is linear according to the input. Okay, so now we're going to be visualizing these transformation matrices in HLSL. So you may be thinking, all right, that's cool, but how do we visualize the theory behind the world view projection transformation? Well, the world view projection transformation goes all the way through taking the coordinates from the model space, which are relative to each individual model, into the clip space, which is the 2D image of the screen. Take a look at this grid. It is yellow when both the X position and Y position are positive. It is green when the X position is negative and the Y position is positive. It is black when the X position is negative and the Y position is negative. And it is red when the X position is positive and the Y position is negative. And this is because the X position is associated with the red color and the Y position is associated with the green color. And when they meet, they are mixed to form us a yellow color. So this is what happens when we treat the position coordinates as colors, and we have no way of visualizing position coordinates except for reinterpreting them as colors. And if we want to visualize the transformations that these matrices perform on the position coordinates, we have to visualize them as colors and pass the position coordinates into the color slots. Yeah, so first we're going to take a look at this. So basically, this in.position.x and in.position.y, what is that? Well, that's just the input position. That's the untransformed position coordinates that are still in the model space. So remember, as I said, in the model space, the axis is centered around the center of each individual element. So each individual element has its own coloration. So for example, in this sphere right here, the portion of the axis runs through the center of the sphere. So the portion of the sphere is yellow, where the x and y coordinates are positive. It is green where the x coordinate on the sphere is negative and the y coordinate is positive. It is black when the x coordinate is negative and the y coordinate is negative. And it is red where the x coordinate is positive and the y coordinate is negative. If we go back several slides, it is because we see that the model space axis is roughly in the center of the object. And if we go here back into the FX composer, so right now we are visualizing the input position coordinates. If we compile, if we rotate this scene, we see that every single object has its own color, which is independent of all the other objects. Now, when we do the world view projection matrix transformation, we get the coordinates in the view space or the clip space or the projection space. This is actually the space of this screen right here. So our axis goes right through the middle of our screen. So any objects that are in this portion of the screen where the x is positive and the y is positive are colored yellow. Any objects that are in this position of the screen where the x is negative and the y is positive are colored green. Any objects that are within this position of the screen where the x is negative and the y is negative are colored black. And any objects that are in this position of the screen where the x is positive and the y is negative are colored red. We can take a look at this by just commenting out this and commenting in this. Now we are passing the output positions to be visualized, so we compile and we see that basically when we rotate it around, the axis stays fixed at the center of the screen, and no matter what we do, if we move the objects around, if you put your finger on it, you would see that the axis is placed in the position of the screen. So this is how we visualize the clip space. It is a two-dimensional image, and we see that the objects are being colorized according to where in the two-dimensional screen they are being located. Yeah, so that's kind of cool. But actually, I would invite you to use this knowledge that you gained, this way of visualizing position coordinates, to explore the coordinates of the world scene and the coordinates of the view scene. So basically, if I comment these both out, let's try it together. I initialize out.color with something, and basically I'm going to do a float for position W, because I want to be able to observe the position coordinates in world space. So I have the input position and I multiply it by the world transformation matrix to get the position in the world space, and then I just can copy this code one more time. Copy this code, place it in here. Now, instead of in.position.x, we just use the world position coordinates. So if we compile it, we see that the objects are colorized based on their position in the video game world. So if we go back, we see that the positives are red and yellow, and the negatives are green and black of the X position. So apparently, this is the negative X position, and this is the positive X position. So we can test our hypothesis that these objects are indeed colorized according to their position in the scene by moving this torus shape right here. If I move it to the left, to the negative side, it slowly becomes a dark green shade, and if I move it to the right, it becomes a red shade. Now if I move it up, the Y position, the Y component will be increasing, and it becomes a bright yellow shade. If I move it all the way down, the Y component is now negative and the X component is positive, so it's a red shape. If I move the X to the left, the X component slowly decreases until it becomes negative, and the Y component is still positive, so it's a green shape. And if I move it all the way down, both the X component and the Y component are negative, so it's a black shape. Me return its position. So this is how we visualize the world space, the objects in the world space. And now we're going to visualize the view space coordinates. I'm going to just replace these variables right here, save, and compile. Now, going back to the slide in which I talked about the view transformation. Recall that the view space is the 3D space from the point of view of the camera. So here we see if the camera is looking down on the scene, it's like a position or orientation, it's looking in a negative direction. So if we go back to here, we see that negative y direction are black and red. And if the camera is looking up at the scene, that means it's looking in a positive direction. So we see that the colors are green and yellow, which are the green and yellow colors in the positive y direction. Similarly, if the camera is looking to the left, all that we see is green, because that's the negative x direction in which the camera is looking to the left. And if the camera is looking to the right, like here, we are seeing the red color appearing, because the red is when the x coordinate is positive. And also we are now seeing this yellow color as we move further and further to the right. So that's just a way of seeing the view of the camera, as well as the world coordinates and the model coordinates, and also the screen coordinates. So this is it. This is the last experiment that I'm having. So in our next lecture, we will see the DXIL code that is generated for these transformation matrices. So be sure not to miss it. See you later.